This is Kyle Welch with RCR Wireless News. I want to thank everyone for attending RF and Fiber Worlds Collide, presented by JDSU. Our presenters today are Brad Getzelman, RF Test Engineer at JDSU, and Nevin Yembresh, Regional Marketing Manager for JDSU. Just a reminder to everyone in attendance that within 24 hours of this webinar, we will provide you with a link to the on-demand version of today's webinar and a copy of the slides. During the webinar, we encourage all viewers to submit their questions via the control panel. Questions will then be answered at the end of the presentation. With that being said, I would now like to turn the presentation over to Brad.
Thank you, Kyle. To basically share with you today, we're going to basically start with an agenda that shares the cell site evolution, distributed RF advantages, and deployment challenges. Then we're also going to cover a few slides on best practices for both RF and fiber, and at the end we'll leave some time for questions and answers. Coax meets fiber as evolution. Starting at the left-hand side, the conventional cell sites has always been to run RF coax cable, generally up a tower, oftentimes a very large coax cable for each one of the antennas being served. As things have otherwise become more distributed and looking for alternatives, fiber has now found its way into the RF world, where we now have the opportunity to run fiber up a tower, minimizing the amount of cabling and the weight that would otherwise be found on these towers, so that we have a remote radio head or unit at the top with the coax in closer proximity to the actual antennas. We've also found that DAS systems are another excellent way to otherwise distribute some of the RF, and we'll talk a little bit more about that later. And then there's also small cells, where a macro site may not be ideal, and they already have the backhaul or the infrastructure there to otherwise carry the traffic, and all you need there for deploying a cell site then is power and a backhaul. And there's a lot of, when I say industry trends towards otherwise going towards small cells. As far as DAS and different configurations, it pretty much all starts from some type of a feed from either the service provider, a donor cell, or just a front haul backhaul type of connection that gets you back into the cloud of the internet. It can be either low power RF or high power RF, and even today we're now starting to see signs of digital CPRIs being a new way to otherwise come into the point of interface, where on a DAS system you have combiners and the master distribution unit, and then various transceivers. The next animation based on the transceivers just goes to show that transceivers can take on a variety of different forms. It can be 50 ohm coax and then have passive splitters going out to a variety of antennas. There's also a wide presence of analog fiber, both strand and pair, that go out to remote units that then converts it back into RF and then goes out to the antennas. There's even some vendors who actually use the 75 ohm coax, oftentimes found in cable TV systems, to actually connect their transceivers up to the remote units. Otherwise, we're now also seeing a migration more towards the digital fiber that lends itself to multiplexing, so that you can otherwise combine multiple fibers onto a single fiber because they are in digital format. And not to be, when you say leave out, one of the other aspects is that we're also seeing that twisted pairs, Cat5, Cat6 type cables can also be used as part of these DAS configurations. I want to also share with you a quick introduction to CPRI. It is an industry cooperation to define the specification for a fiber optic interface between radio equipment and the actual radio equipment control. The three different parts or the information flows are the user plane or the data, control and management plane, and synchronization. But keep in mind that while these are multiplexed over the interface, some of these are in fact proprietary interfaces as to how they actually work and encode the various RF over CPRI and other tasks that can be performed over that standardized link. Distributed RF advantages. We're going to share a couple slides that otherwise kind of touches upon why you otherwise want to distribute that RF. And it boils down to signal quality to the end user and or system capacity. As of today, the DAS and small cells appear to be the best alternative to beam forming antennas. This is actually covered in 3GPP specification, where the technology originally seeks to direct the RF coverage patterns more precisely to follow the subscribers themselves. But since that really has not fully matured or become economically feasible, what they found is that by placing multiple antennas closer to the end users and creating smaller RF footprints, you can ultimately improve the signal quality. Very similar to trying to get that signal onto a wire as quick as possible, which is a little bit more of a controlled environment. But this only works well if the power levels are well balanced according to the surrounding antenna coverage, which means that the best performance capacity is ultimately going to be accomplished when there's minimal adjacent antenna overlap and multipath signals. So the RF coverage should ideally create high-quality, dominant signal covering where subscribers congregate. But I also want to touch upon one of the key advantages to DAS systems. Our components are often reusable as the technologies otherwise continue to change and evolve. This is a fantastic slide that one of our partners and associates that we've worked with in the past basically said it all. It's all in the scanner, and they basically gave a quick chart of PCIs for LTE that are within 5 dB of the dominant server. And what the takeaway was, and we had conversations about this before, and he basically just provided me kind of his own data that he had collected to provide that perspective. And in the end, he adamantly says or shares that basically he would much rather have a single sector with a service RSRP of a neg 80 dBm than having two sectors with an RSRP of a neg 60. Jarrett basically points out, and you can see clearly in this graph, that even though you have strong signals, when you have two of them, your SINR and quality greatly decrease when you have multiple sites competing for the same space. So let's talk a little bit more about deployment challenges. There's a few of them. So to begin with, think of the considerations before you start with distributing your RF. And that is, you have to baseline the existing coverage relative to the respective bands and technologies of interest, meaning that if you're doing coverage and you're looking at this, you oftentimes have to take into account all the technologies, all the carriers, and into account while you're otherwise doing this type of planning work. New RF coverage should complement and not compete with existing coverage. Again, trying to minimize that overlap between adjacent sites and sectors. Begin with, the existing coverage can be permanently changed, yielding to better RF planning, meaning that it's not uncommon that we've seen where macro sites will actually be turned off or greatly down tilted, or the power is greatly reduced when a DAS system is especially employed within a large venue. There's also considerations to be given during major gatherings and crowd movement. Can the coverage be dynamically changed? We've clearly seen that during Super Bowl events, that while crowds gather on the outside of the stadium, you're wanting to otherwise manage the RF there, but as they move into the stadium, oftentimes it's very advantageous to change the coverage of the macro sites that might be covering those areas to otherwise give preference and coverage to the DAS inside of the stadium. But also, in terms of consideration before you start, think of the benefits of predictive modeling. Oftentimes, by putting up temporary transmitters and antennas, you can better model the actual environment that you're otherwise putting this distributed antenna system into. But ultimately, the bottom line here, and the last item, is that the RF licensee, meaning the service providers, must approve of whatever you're doing because it still is licensed spectrum that they own. This slide on control your RF environment is largely taken from my background as a test engineer, that I focus on controlling your environment as part of a test. But in this case, it could also be extended to the RF and understanding the different aspects which can and will affect RF quality. The signal quality ultimately comes down to the components and the installation. If you use high quality components and approved or installation methods which are recognized by the industry as being some of the best practices, this will ultimately provide one of the best signal qualities. The actual antenna placement types, this is going to obviously affect RF quality. The power levels, including noise, and when I refer to noise, I'm referring to the noise that can be otherwise generated by adjacent sites and sectors. Now, these last 5 items that I have shown here, the building materials, geography, time of day, vegetation, weather, can all affect RF quality, but obviously these things are a little bit less of your control, but you do have to take those into account as part of your RF planning. The three squares here, as far as access, visibility, and control, again takes back to the test engineering roots that I have, where access or testability begins with access. You have to have some type of test points. Now, arguably, RF can be, when you say access, through an antenna. But sometimes you're looking for a little bit more control and better environments when you're otherwise trying to measure performance. So physical test points also have a unique and very beneficial advantage. Visibility is pointing towards the built-in as well as the external test equipment, meaning that what do you have to otherwise draw your attention to the details. Details of either function and or performance of the device or system under test. And the third part of testability is control. And for most, it comes down to the level controls. What control do you have over the device under test or the system to otherwise control the levels? But it also has to do with different test modes. You can control the device to otherwise push it to full power to make sure that under full power load conditions that the signal will still maintain its signal integrity. Oftentimes I like to think of the old radios in your older automobiles that they didn't have a volume control, meaning that it would actually allow you to turn it all the way up when in fact it was very distorted. Like think of RF as being the same conditions as well as fiber environments and other electronic environments that if you don't have control over those levels, you can otherwise degrade the performance. Do you need to test? Why and when? Basically, you need to go what you're getting into. It starts with the cables and antenna analysis, making sure that you have a very sound physical layer to work with. Second is the spectral measurements, knowing that you're otherwise going into clear spectrum and that you don't have any competition that otherwise shouldn't be there, because it's going to be much easier to find before you deploy a site than after you turned on a site. And in fact, could result in service disruption if you have to turn off the site to otherwise find what may otherwise be lurking behind. But then the third part is the signal quality measurements, knowing that you can actually look at the modulation quality, the power levels, as well as the timing to understand that you have in fact met the expectations of the industry to reach or to achieve the highest levels of performance. So doing it right the first time requires, again, first, test before you start, establishing that baseline. Second is, oftentimes best served as design validation before installation, putting up those temporary transmitters, actually refining the modeling that you're doing for a propagation so that you otherwise don't actually go through the construction phase before you actually know what the effects are going to be based upon the antennas and the placements. Test while you install, that's all about being preventative. Making sure that you're doing things right the first time, that you don't have to otherwise spend the time to go back and try to isolate what may be wrong if you see problems after you get it all turned up. Setting uplink and downlink path losses and gains. Again, this comes back to that dynamic range. Ideally, you want to be in the middle. You don't want to be too weak and you don't want to be too strong. Just like your stereo system, once again, as an analogy, when you turn down the volume, you don't expect to hear anything that you don't otherwise expect to hear. At the same time, when you turn it all the way up, you don't expect the sound to be distorted or have anything that otherwise shouldn't be there. And finally, test when you're finished. That's the acceptance testing. This is generally where the signature comes that allows you to get paid for whatever work that's being done, or if you're paying your contractors to make sure that they've done a suitable job and they've in fact provided the evidence that they've done the task according to everybody's expectations. But the bottom line is you have to continue to monitor. Stuff happens and you do have to make repairs. But for the challenges for deployment, what's happening is that as the industry evolves and they're looking for better and better technologies to accomplish the act or the engineering feat of distributing RF, you now take on a variety of different facets, whether it be fiber cabling, Coax, either 50 or 75 ohm, that can be part of these distributed antenna systems, Cat5, LAN cables that can otherwise be part of a manufacturer's product line and what they use. And again, 75 ohm Cat5 are oftentimes very familiar to electrical contractors and people doing work inside of buildings. And they can also be very small and not very, when you say noticeable in the process. But ultimately, you still have your RF and RAN environment. That's the ultimate where you have to verify your antenna operation, the macro cells, the DAS cooperation, to make sure that everything is basically working in unison. And there's a number of advanced topics. Again, the CPRI is part of a protocol which is now starting to make itself more and more, it's just beginning as far as the deployment of distributing RF. Now, this next slide is basically trying to draw attention to demarcation, the working groups. from construction to maintenance of three basic types of sites and deployments. And looking at the legend at the bottom where you have core, fiber, coax, and RF, what you'll see in the animation of this slide is that this actually starts to show that, yeah, on the commissioning and backhaul, you have a technician that otherwise is responsible oftentimes for that aspect. When a typical construction of a cell site, you have a construction contractor, tower crew that does the climbing, does the RF cables, and that's simple, coaxial work and make sure everything is terminated correctly. But as things evolve, you're now starting to see that in small cells, the introduction of fiber. So the small cell tech now has responsibility not only for the coax, but also for the fiber that they're deploying. In a construction where you have DAS systems, where you have system integrators and contractors, now they have not only the fiber and the coax, but also they're oftentimes responsible for doing the RF aspects of it, whether it be the pre-walk and the baselining or the afterwards, but ultimately they are responsible to basically cover all three of those areas. And then the actual commissioning, whether it's the network equipment manufacturer or the cell site technician, again, they too oftentimes have to deal with all three, fiber, coax, and RF, in that actual commissioning of the site. And then ultimately it comes out to the optimization, the system performance engineers. And although their largest focus is on the RF and its coverage, they too are now becoming more involved with the core, because oftentimes the limiting factor of many of these 4G systems is no longer the RF, but in fact the backhaul. So system performance is now taking on new roles of also taking and learning about how the core can otherwise impact the throughput. And ultimately, the maintenance of the cell tech has now become, when you say, responsible oftentimes, once it's been commissioned and turned on, for all four aspects, whether it be the core, the fiber, the coax, or the RF. When they have a problem or they detect a lower than expected throughput, knowing where to start with understanding exactly where that limitation may have otherwise come from. And if they understand how it was installed and the components they used, hopefully that will give them confidence to know exactly where to look first in trying to understand exactly what the problem is. This is a simple case study where we've actually seen, as we were basically demonstrating one of our products, and the customer's getting very excited about what they could see as far as visibility, again back to testability of a BTS. All of a sudden they stopped and they paused and they looked at me and said, "Can I also measure the DAS system?" Well, the first concern I had was, is it a neutral host? He said, yeah, but he says, it's a stadium, there's nobody here right now, we can turn it off, we can make a connection into the antennas, and we have an attenuator so we're not damaging the test equipment, and we can look at what's coming on the other end of the DAS. Well, this is one of the first revelations that, as you can see at the bottom here, the modulation coming out of the base station was quite clean. And the reality was is that many of the tributaries of the DAS system, we actually found degradation in the signal quality. And this is something that is prevalent and can happen within a DAS system. Not only can it happen to the signal quality, but we've also seen where cables have been swapped, meaning that you don't have the MIMO that you expected. And there's different levels of what kind of impact that can have to the end user, or simply just a diversity alarm where you may be replacing the wrong antenna. We've also found on these case studies where we've also seen timing of the two transmits for MIMO are in fact not within the specifications of what 3GPP requires. So looking at how a signal propagates through a DAS system and measuring at the other end is the focus of the next slide. We have a customer who otherwise was very interested in actually baselining from a reference point out of the base station exactly what the signal looked like coming out of the E node B and the BTS. And then they wanted to otherwise look at all the various tributaries of the DAS system to determine what otherwise might have changed, whether it be the power levels or the modulation quality or the timing. So actually we've come to find out it can be very beneficial to otherwise understand, as far as control your environment, how well has the distributed antenna system otherwise been able to accomplish maintaining a high quality signal all the way out to the end. So again, this is just one way of otherwise looking at how you can otherwise, as far as challenges, meet some of those challenges and understand whether or not you've reached your intended goals. To continue on deployment challenges, you'll also find installers now need to support multiple technologies, whether it be legacy, 2G, 3G, but also Wi-Fi and even public safety. We've heard that there are municipalities, which are actually putting into their requirements for building codes that they otherwise, over a certain size of building, that if you're installing a DAS system, you must also include public safety bans for emergency responders. Challenges now is that instead of having multiple tools, each one that has a different function, tools that can support both RF and fiber oftentimes are advantageous to help in moving this forward. Simplified usage is important to speed up the cell site installation, but ultimately having a birth certificate of the cell site to the cloud so important data is not lost is oftentimes key. And this is more or less part of the record keeping of exactly what took place at the time of the installation and what's known versus what's unknown. When troubleshooting has to take place, oftentimes these records can be very important to understand and be easily accessible to understand where to start as part of the troubleshooting. On deployment best practices, we basically have a few slides that we'll share with you on the RF aspects of it, and then we'll delve a little bit deeper and do a little bit more as part of the fiber, as part of the second part of our agenda. On test solutions for radio access network, I believe that the service coverage is one of the most important parts of doing a RF design, and that's actually using actual users' handsets to verify coverage and throughput, because oftentimes this is the best way to relate to those who are otherwise in ownership of real estate or management, to help them understand exactly what's taking place using terms or measurements that they might otherwise be familiar with based on their own day-to-day usage of technology. But I'm also a big fan of the drive test receiver. Drive test receivers are special purpose, meaning that they have bandpass filters and pre-selectors, which give a much more realistic representation of how the handset or the base station would otherwise see the spectrum. And this is very important when otherwise measuring, but the other key advantage of these is that a drive test receiver oftentimes is very, very useful in doing multiple bands and multiple technologies at the same time. So they're great at multitasking. In the next area, as far as cell site performance, I'm a huge fan of base station analyzers, especially when they provide me levels of visibility and details into the signal analysis. In fact, if I was troubleshooting a base station, that's probably one of the first tools that I'd otherwise want to have at my disposal to isolate exactly what the problem is. They're very myopic, meaning that they can go to great levels of detail, but oftentimes in terms of multitasking, they're not nearly as advantageous as a drive test receiver because they don't multitask quite as well. But again, that's not their purpose. Their purpose is to make sure that the base station is in great, when you say health and well-being, so to speak. Cable antenna analyzer, this is for most people who are doing simple installations and doing the mechanics of things, as well as fiber test. Again, back to the mechanics of the actual installation, because it all starts with the physical layer. Just like your house has a footing, literally the cable and the fiber that you're deploying is part of that footing. If you don't get it right, it kind of upsets the balance for everything that goes on above it. And then ultimately onto the wireless protocol test. As a test engineer, I have a great deal of respect and admiration for centralized monitoring, trying to find as many faults with as few tests as well as test points as possible. So keep in mind that call performance, measuring it from protocol, is a great way of otherwise getting that first level of fault detection and knowing that there's a problem. So understand that there's a variety of tools and a variety of tests that can otherwise be deployed to otherwise characterize what's going on with your RF system. This is a product table that just goes to show a product portfolio of a family of products that JDSU has known as a CellAdvisor. And this just goes to show that with the different colors that we're using on the left-hand side here, is that most of this is based upon the blue, the RF, the cabling. What's going on with that? And we have products, again, on the cable antenna analyzer that have different frequency ranges, but also some have single port for reflection, return loss, distance to fault, but others have two-port, which are excellent for characterizing literally anything that has two RF connectors, including if you have a repeater, a donor antenna as well as a receiver, a serving antenna. You can measure the isolation, very similar to taking a microphone and putting it in front of a speaker. You don't want unnecessary feedback loops on your RF system. But this table is probably one of the best ones to otherwise communicate or convey, based upon your responsibilities, what tool may be best suited for your application when it comes to testing either optics, fiber, RF, or air interface. And then you can also see here at the bottom that for logistical reasons, we've also added Bluetooth control and StrataSync to some of these products to otherwise help in managing as well as controlling devices remotely. So all good things as far as understanding how to otherwise approach the testing of an RF environment. This last slide here for myself is otherwise leading into basically how JDSU has taken upon that since fiber has become a big part of RF installations, that it made all the sense in the world to otherwise starting to combine our RF test tools, which are some of the best in the industry, with our RF test tools, which are quickly becoming recognized as some of the best in the industry. And we've actually earned a couple of different awards for that, and we're quite excited about it. So with that, I'd like to turn the presentation over to Nevin.
Hi, my name is Nevin, and I'm working for the cyber division of JDSU. And I'm going to be talking about the proper way to deploy the fiber. But I'll start a little bit with just kind of basics of fiber because I don't know what kind of audience we have. So I apologize if you're already familiar with all of this. For fiber to the antenna, the fiber that is installed depends on different configuration. Can be multi-mode in single mode. As you see here, the difference in the performance of these fiber types will determine what fiber type is used when and where. The single mode fiber is working on longer distances. Multi-mode fiber is working on a shorter distance, but it's easier to deploy due to the core size and not being sensitive to dirt. And we'll talk about it a little bit later. So and here you will see the inside of the fiber connector, where two connectors are meeting. This is an example of the LC connector, where the ferrule connected through alignment sleeve, and that alignment sleeve basically aligns the core of the fiber so the signal can go through. That physical contact of the two fiber is basically the weakest, most problematic point in the fiber optic deployment and fiber optic network. So what makes a good fiber connection? So we call it 3 E's, which present 3 major things that are influencing fiber connection. Perfect core alignment, physical contact, and pristine connector interface. So if you imagine this like just a garden hose, if you connect those 2 garden hoses together, if connection is good, then the water will not leak. With the alignment sleeve being improved recently, the core alignment and physical contact is not an issue anymore. The pristine connector interface is basically what is making the biggest headache in a fiber optic deployment. So, as mentioned here, contamination is #1 cause of troubleshooting in fiber optic network. It basically, if its connector is dirty, that makes the back reflection, insertion loss, and it can damage the equipment. Visual inspection is the only way how to make sure that the end face of the fiber is clean prior installation. So what is kind of the point in here, and there was one of the questions in the panel, why the service providers are asking for the end face inspection. So a lot of people are trusting the dust caps as the protective protective interface from contamination. Dust caps should be called, they are named wrongly. They should be called protective caps because they are good in physically protecting the interface of the fiber. As much as they can keep the contamination away, they can keep contamination on fiber. So here you see the OTDR trace, and that shows what is the what happens to signal when the connector is dirty. The OTDR trace shows the 3 different connectors in the link. First 2 are clean, and the third one is dirty. And that I don't know if you can see, but there is a little particle of dirt in the core of the fiber that is creating 4.87 dB loss for that particular connector. So now, if the dB requirement, 3 dB requirement for your link is required, then pretty much this dirty connector, which is not significantly dirty, but it's on the core of the fiber because the contamination is on the wrong spot, it will basically fail your link. So as Brad mentioned earlier, there are 2 the best practices of handling fiber should be proactive inspection and cleaning versus reactive inspection. You will definitely, if you're handling fiber, you will get a fiber that will probably be dirty. Not only that can be dirty from your supplier, but it can be contaminated while handled. So when you take your dust cap, you can touch it with your finger, and there you go. It's contaminated. Now, since contamination is going to be probably present in there, cleaning after inspection is the logical kind of step that it's going to follow. And if that cleaning easily cleans that fiber, then you not have there is no problem with that particular fiber, because that, as mentioned, fiber can be contaminated in handling and in transport. Now, what majority of people do is basically connect the fiber and hope it's going to work. After you connect the fiber and there is a dirt, and dirt is, if you can imagine it like a rock, while fiber is made out of glass. It's a huge pressure where the 2 connectors are connecting. It will basically create the damages on that interface. So if you clean, if you plug in fiber and that fiber is not working, then you unplug it and try to clean it. The connection, the dirty dirt might be removed, but the pits and chips that contamination left on the interface of the fiber will be permanent there, and that will create the air gap, which will basically degrade your signal performance, create insertion loss and back reflection. So those are the reasons why proactive inspection is better than reactive inspection. Now we're going to go into the simple procedure how to handle fiber. And we call this procedure inspect before you connect. So you inspect the connector, and here is shown only just a bucket, but it should be inspected, not only bucket, it should be inspected patchboard, should be inspected the test equipment. If you have a dirty test equipment and you have a dirty test lead that is contaminated, and the test is performed with your network or customer network, you will be damaging that connector, that network, that fiber connector in the network. So inspect first and determine if it's clean. If it's cleaning procedure and reinspect it again. And continue this procedure till the connector is passing or is satisfactorily passed. Right now, the software, inspection software gives you easy pass-fail, so that's easy to determine if you have acceptable or not acceptable. A lot of people are asking a lot of questions of why shouldn't I just clean and not inspect? Well, several reasons for that. First, what if you have a clean connector? Then you're using the cleaning tool and basically wasting the cleaning tool. Second thing, the no cleaning tool is ideal, meaning that it can introduce the contamination on the fiber, and the only way to verify that is by inspection. Third thing is, what if that connector is damaged? That connector, probably before it was handled by you, was handled by someone in manufacturing, then system integration, pulling the cable. So probably you're fifth or sixth person who's touching this fiber. I personally don't believe that everybody before me followed the right procedures, and that I know that the fiber is clean and not damaged. It's better to be safe and not assume someone else's mistake. Doing inspection after cleaning and making sure that it is acceptable will protect, for example, a contractor who is getting the bad fiber from the supplier, or the service provider who's getting the work done by contractors to make sure that the fiber that's going to be turned on later down the line will perform as it should. So, the second, just to repeat one more time, the contamination and dirty connectors is #1 problem in fiber optic network. And so if you're installing the fiber, that will be the weakest point. The second one is the microbends and microbends that are caused. Microbends are caused by the external pressure, usually when the water freezes and puts the pressure on the fiber. Microbends are a little bit more common because in the past people would zip tie those cables, so that would change that fiber, and or one of the contractors showed me the picture the other day where the fiber was positioned that way when he closes the patch panel, that it would push on the fiber, and it was bending the radius so that the fiber would not perform properly. These are the installation of the fiber optic network in the cell site. These are the kind of couple of test things that some of the service providers do. We call that Tier 1 certification, which includes just the loss and inspection. The first thing on the list is check fiber connectivity. That is the third issue that is happening in fiber with fiber optic antenna deployment. That correct fiber is plugged into correct port. If you're doing the insertion loss testing or OTDR testing, those lengths are the same, and it's going to be hard to verify if that you are really on the fiber that you should be. So visual fault locator, even though it's made something basically detect bends, it is used as the verification tool that I'm on the right fiber and I'm plugging in the right connector. Then second thing, the biggest issue, end-phase inspection and quality of the end-phase. Then work doing the insertion loss testing with the light source and power meter. So the benefits of the Tier 1 certification is it goes easy. It's easier to be done. And it gives you easy pass-fail test for that particular link, usually under 3 dB, and is good to go. However, does not give you the granularity of the of that link. So we go into the Tier 2 testing. which some of the service providers require. Again, check fiber connectivity, that it's plugged in the right place, check interface of the fiber, that it's not damaged, measure fiber link channel length, and then measure the individual events in that fiber. So if there is several distribution box that the fiber is connected with the OTDR, it will be able to verify that every single connection, every single fiber link is per standard. Meaning, with the tier 1 testing, it can be under 3 dB loss, but one of the connectors in that link can create, as we saw on the previous slide, the one created 4 dB. But if the connector is borderline and it has a 2.5 dB loss, that test, that link will probably pass the tier 1 test. But with tier 2 testing, you can pinpoint the weakest link, and maybe with degradation over the line, over the time, that 2.5 dB fiber connector will cause the trouble down the line. So that's why some of the service providers require the OTDR test as well. OTDR is used for the troubleshooting because it easily can point it out where that problem is, versus the tier 1 testing with the power meter and light source, which is just research. So these are just examples. Some of the tests that we recommend in different applications. This is the outdoor DAS. Due to the different configurations, they use one fiber. They use the 1515, 1310 as upstream and downstream wavelength. And the length of the fiber are over 20 kilometers. There is probably more spikes in those and more connections. Recommendation is to, besides the interface inspection and checking that the right fiber is connected to the right link, is OTDR test. So the example of the indoor DAS, which is similar to the cell site deployment, the lengths are shorter. Sometimes you have the pair TXRX fiber. You can define single mode and multi-mode fiber here, and the procedures of the connector interface, verifying polarity, continuity, measuring optical link loss might be sufficient for the installation, while for the troubleshooting, definitely OTDR would be the right tool to determine where the problem may occur. So the question comes after, what do you do with those tests after they are done? Our equipment can provide the PDF report, that's first certificate of the installation, that will enable you, if you're a contractor, to get paid by the provider, or if you're a service provider, to know what exactly is installed and how it looks like for your record that can be used down the line if there is any issue. So what do we usually suggest is to have some capability to store the data for the verification down the line if there is any issue. To use, and we have product strategy that works on all our platforms. Besides collecting the data and managing that data, one of the really good features is configuration management, meaning you probably will do indoor DAS, outdoor DAS, cell tower installation. All those different tests will require different test parameters. With our strategy, those profiles, specific profiles, can be communicated to your workflows on the field, so it's easier to manage basically what kind of jobs they need to do, and then easy to manage what kind of test results you get. Or if you're a service provider, it's you can compare easily the test data that's received by contractor with the test data that your technicians are doing if there is any issue. In addition to that, you can do asset management and upgrade the unit, new firmware and everything else. So with that, I will close this and open for questions.
All right, thanks, Nevin and Brad. We have time just for a few questions, but I want to let all the attendees know that both of our presenters today will get a list of all questions asked for any that we did not get to. So the first question that came in, does JDSU support CPRI testing?
Yes, we do.
Okay. And then what are the primary differences between IDAS and ODAS?
Mostly the power levels. Basically, indoor DAS is generally a lower power level. Outdoor DAS is generally a higher power, very similar to lighting and sound systems. You basically have to consider the environment, but basically its enclosures is the other aspect that tends to be considerably different between the two.
Okay. Next question coming in. Why do some cell vendors require fiber scope testing when passing DB test is sufficient?
So I hope that I addressed that. So the end phase connection and basically contaminated fiber is the #1 issue across the board. So DB loss of the one particular connector in the link may be the weakest link in that fiber link, which may pass a DB test, but eventually cause the issue for the service provider. That's why they kind of want to protect themselves and have that documentation to know what kind of link is involved.
Okay, thanks. And I guess as a follow-up to that, we had a few questions asking about how you would actually test a CPRI link.
First of all, you need a coupler that would otherwise provide a tap into the fiber. The second part of it is that CPRI interfaces, although there is a standards body which otherwise governs some of the framing of how that works, the other aspect is that having access to the proprietary details of the actual user plane. But it starts with a fiber coupler, and our instrument, for example, for RF over CPRI that we're beginning to proceed through trials and demonstrating to prospective customers that are showing interest in CPRI, is we have an RF over CPRI where we can actually take and today currently tap into and show the spectrum data that otherwise is being received or transmitted across the CPRI interface. So this is in terms of access, as from testability that I mentioned before, it starts with a mechanical test point, which again is a fiber splitter coupler. The second is the visibility, and that is again having proprietary access to the contents of the payload and actually being able to demodulate or to be able to show that in a way that's meaningful to help understand what the problems might be.
Okay, thanks. What type of fiber characterization is required for CPRI?
Fiber characterization, what I've recently experienced is that it starts with the mechanical interface, making sure you have the correct LC, whether it's an APC connector, and making sure you have everything properly set up for the mechanical level of the interface. As far as characterization and understanding the quality of the CPRI and the packets, I would say that probably goes best to our 5800 product line to otherwise characterize the quality of the CPRI timing and the protocols.
Okay, thanks.
Hope that answers the questions.
Also, I guess this is more of opinion-based, but is PIM testing necessary?
That is a question I've heard quite often. PIM testing is excellent for performance quality metrics, understanding exactly how good the quality of the parts are, as well as the installation. But ultimately, what I've heard time and time again is that it's most important when it comes to higher power levels. But provided that you're using high quality materials and installation, you've ultimately minimized the risk, but then you ultimately then have the antenna placement, which is the next highest concern. Because whatever's in front of that antenna can in fact lead to reflections or passive intermod, which causes interference to itself. But one of the things I do recommend is that even before you employ the services of a PEM tester, that when you're going through the process of return loss, distance to fault type measurements, it's very common with PEM testing that they do a tap test with the handle of a screwdriver. The same thing can be used when you're doing a reflection test, because if everything is mechanically sound and tight, when you're doing that tap on the various connections, you should not see movements in the traces on return loss. If so, I suspect that when you go to do PEM testing, you would have the same outcome. So oftentimes before you do PEM testing, return loss reflection is oftentimes a good place to start with tapping, but it ultimately comes down to what exactly is the power level. Another school of thought is that if you actually have control, again, that third part of testability, over the base station to employ OCNS test mode, which is orthogonal channel or code noise simulation, to push amplifier to its full wattage. If you can do that across all of the transmitters that are otherwise present at a site, they too can serve as a high power source, and at the same time look at the uplinks to see whether or not there's any interference that's being created as a result of it. So there's a variety of different ways it can be offset, but PEM is still a great performance quality metric for characterizing mechanics and the quality of the materials.
Thanks. And to go along with that, another question we had come in is what kind of interference is analyzed by the JDSU test unit?
Generally, it comes down to spectrum analysis, kind of looking at different ways of presenting spectrum data, whether it be through a timeline or through a spectrogram. But the other key points of using the JDSU equipment and any spectrum analyzer for that matter is understanding how to get the most from it by understanding resolution bandwidth, your spans, the type of antenna that you're using to try to increase that dynamic range, and the DANL, the noise level of the spectrum analyzer itself. But it also comes down to knowing the basics to get the most from seeing that interference, and reducing the noise floor and using the max hold, min hold. We've done webinars before, we can do them again, that otherwise point to those basics of how do you get the most from chasing down interference and using a spectrum analyzer to accomplish that.
Okay. I think that's about all the time we have for questions at this point. I want to thank everyone for attending RF and Fiber Worlds Collide presented by JDSU. And I also want to thank both of our presenters today, Brad Getzelman, RF Test Engineer at JDSU, and Nevin Yembresh, Regional Marketing Manager also at JDSU. Thank you for attending, and have a great afternoon.